If you recall, what we're trying to do is find a way of describing electrons in the atom so that we can then get not a visual picture of where the electrons are, but some sort of accounting of where the electrons are and what kind of energy they have and how they're oriented and how they're positioned, so that we can start to understand atomic properties and then translate that into molecular properties, starting with bonding. So what we're after today is continuing to move in that direction. So our last stop was orbital box diagrams, and I'm going to do the orbital box diagram for oxygen, and it's here, where we've got electrons in the first energy level in the s orbital, electrons in the second energy level in the first sub-energy level, the 2s orbital, and then 4 electrons in the set of orbitals that are in the second energy level, and then the second sub-energy level, the L equals 1 sub-energy level. So it looks like this. Okay, I want to start using that kind of designation to translate my orbital box diagram with the arrows into some other kind of notation. So if I were to look at that orbital box diagram and count the electrons in where they are in terms of the energy level and the sub-energy level, I could write this, where I've got 2 electrons in the first energy level s orbital, so the 1s2, 2 electrons in the 2s2, and 4 electrons in the 2p orbitals. I really did a bad job of that. Art is hard. Okay? That represents the electron configuration. So sometimes we'll do orbital box diagrams, sometimes we'll write electron configuration. What we're after today, though, is using the periodic table to come up with the electron configuration. If you look at the periodic table, you notice there's these sections. It's almost like, boxes or rectangles on the periodic table. So I've got 2 tall columns on the far left, I've got taller columns on the far right, I've got these middle columns in the middle of the periodic table, and then down on the bottom I've got this other box that really should fit up in the middle somewhere, but that would make the table too long, so we'll section it off and make it its own thing. What we're going to do is we're going to set up a periodic table like this, and a couple things you'll notice right away. Number one is I moved helium. We're not actually moving helium anywhere, it's just that in order for our sections of the periodic table to work well for electron configuration, it's going to fit better there. I've identified the rows 1, 2, 3, 4, 5, 6, 7. I've identified the 2 on the very, very bottom where they would fit in, and I've also labeled on this periodic table a couple of other things. So that first tall columns, that first section, I'm going to call it the S block, and N equals row number. And then I've got a P block over on the far right where N equals row number. The D block, short ones in the middle, is N equals row number -1, and the F block down on the bottom is row number -2, N equals row number -2. So how do we use that? I've also got a couple of columns, the chromium column and the copper column. I've got them colored a little bit differently. We're going to do something with that later. Okay? And then, as I mentioned before, I've got the rows numbers indicated, partly because I've also said something about N equals row number. So row number is going to be kind of important. Okay, so how do we use it? Well, let's start with germanium. So I'm going to write the electron configuration for germanium, and what I'm going to do is I'm going to find germanium on the periodic table. Good first start. Then what I'm going to do is, in the same way I started orbital box diagrams by starting with hydrogen, I'm going to start electron configurations with hydrogen. So I'm going to work my way from hydrogen to germanium, going across the periodic table, doing exactly what it tells me to do. So I start across the first row, and I work my way that far. As I get across the first row, I'm in the first row, I'm in the S block, and I've got 2 boxes. So that translates into 1, first row, S block, 2 spaces which represent 2 electrons. Then I'm going to go across the next row. Well, to start across the second row, I'm going to start in the S block. So I'm going to do a similar kind of thing. Second row, second energy level, 2s2. S block, 2 electrons, 2 boxes. Then I'm going to jump the gap and work my way across the next section. Well, that next section is also in the second row. It says P block above it, and N is equal to the row number, so that's going to be 2P, count them all the way across, 8, 6, 2P, 6. Math is hard too. Then I'm not at germanium yet, so I start the next row. Next row is going to be a similar kind of thing. Now I'm in the S block again, so it's going to be 3S2. Then I'm going to jump across the gap, and I'm going to do it all again. I get all the way across that P block. N is equal to row number, so I'm in the third row. N is equal to 3, 6 spaces, 3P6. Work my way across the next one, 4S2. Now, as I get into that next block, the next block is a little bit different because now with that yellow block, if you look, it says D block, and it says row number -1. N equals row number -1. So that is not a 4, it's in the fourth row, but it's actually a 3D. Count them all the way across, 3D10. Getting closer to germanium. I've got 2 more to go. As I go into the next section, I'm back into the P block where N is equal to row number, so that's going to be N equals 4. P, and I got 2 spaces to get to germanium, 4P2. Okay, that is a description of all the electrons, their energy level, their sub-energy level, and how many there are. So I put it all together and I get this on the bottom where it's just writing out how I got to germanium. That looks really long, so the question would obviously be, is there a shorthand? And the answer is yes, there's a shorthand. What we do for the shorthand is we take the previous noble gas and we put it in square brackets, and that represents the, let's call it the core of the atom or the electrons, and then we write the remaining row. Okay? So germanium would be previous noble gases argon, and everything after argon, well, it's 4s2, 3d10, 4p2. Okay, so if you wanted to do something like that for bismuth, we would find bismuth on the periodic table, we would find the previous noble gas, which is xenon, write that down in square brackets. I'm picky about the square brackets, make sure they're square. And then work my way across the last row. So the last row is going to be 6s2. Oh, if I go into that next one, then I've got that little star, there's a little notation there that takes me down to the bottom, very bottom, all the way across there. So I have 5D1, then I'm into the others. That is row number -2, N is row number -2, so that's a 4F, F block. Count them all the way across, 14. Then I'm back to finish off the 5D block with 9 more electrons. Then I can get my last 3 electrons out of the 6p and give me bismuth. Okay, and we could do one of 2 things. We can write it out exactly as we saw it, or you could combine the 5d electrons into a total of 10 and write them together. I have no personal preference, whatever works for you. You'll find some sources will put these things into order of smallest n value, working their way up. So you'd see a 4f14, 5d10, and so on. I'm not looking for that. What I want is the right number of electrons in the right place. If you want to break them up, if you want to combine them together, if you want to put them in some fancy order, all of that's fine. I'm looking for a total of 6s2, 5d10, 4f14, and 6p2. However you get there, that's fine with me. Okay, earlier we identified the copper and the chromium families, and we're going to leave them for now. Okay, we've got enough to worry about. We'll come back to them another time. What we'll do to make sense out of what happens with them is we'll look at the orbital box diagrams and a couple of other things that we already know. Okay, so shorthand electron configurations, that's what it's all about, and we'll talk to you another time.